Thank you, Ji Wong. Hi, everyone. First of all, I'd like to thank you, Mats, and all the others involved for inviting me. It's really a pleasure giving this talk. I think CORC is a great idea. I really enjoyed the discussions when we met a few months ago. So I think this is a very, not only a very timely topic, it's a very important topic, I think, for the human society in general. Today, I would like to give you some examples of our research, but also some a little bit probably more provocative type thinking. I try to make the talk not too special, so it also addresses a little bit a broader audience, and I hope you find it interesting. If you have some questions afterwards, you can, of course, directly ask. You can put it in the chat, or do not hesitate. If there is a question arising to a later stage, send me a mail. It's very easy. My mail address is matthias.beller@catalysis.de. So why do we have to think about resources, the use of resources? I think you all know very well, and this is also a main topic of CORC, of course, that one of the biggest problems which we face, apart from all, let's say, the local politics and issues, that in general, mankind is using more resources than are rebuilt at the same time. So since several decades, we run out of equilibrium. If you calculate, let's say, the resources which can be rebuilt within a certain time and which are used in that time. And I believe also most of you are aware with the concept of the so-called country overshoot day. So if you're not, I recommend you can look at the website of the Earth Overshoot Day. The so-called country overshoot day is a statistic date in which basically the resources by country have been, let's say, used, which can be rebuilt in that country at the same time. And if you, most of the time, we believe in Europe, we are, or in the Western world in general, we are perfect, we are using resources very efficiently and so on. But if you look more carefully, actually, if everybody in the world would live like people in Germany, our resources would be used last year, this year is not so much different, basically on May 4th. And in other words, this would mean we would not need one Earth with respect to resources, we would need more, basically more than two Earths. For most European countries, the situation is not much better. So you might be also surprised Denmark is here, for example. US, Canada are even earlier on. So if everybody else would live, let's give, for example, like people in Qatar or Luxembourg, we would need 6 Earths. So it's clear from this statistics that, of course, we want a working economy, we want to create jobs, we want to have good living conditions for everyone, but at the same time, we have to be in equilibrium with the use of resources, because otherwise this would not work. And this is our vision of sustainability. Like many others, we have created this already, I would say, more than 15 years ago. And it's a very, let's say, general type thinking, and you might have seen better pictures, but the general thing is, of course, you start using available resources. That means sunlight, wind, hydropower, renewable energy in general, available resources like water, specifically seawater. As carbon sources, you are using waste, bio-waste, or carbon dioxide from the atmosphere or from industry in a more concentrated form. And with these resources and with available renewable energy, in principle, you can build up all the goods which we are using today and which make our life much more pleasant. And in fact, often people think this is a blue sky vision. In fact, it's not. Most of the things can be done, but the problem why they are not, let's say, implemented in our economies and our industries and our societies, the problem is, compared with the currently existing technologies, they are still too expensive. And of course, there is two things, or two general ways how to implement them. Let's say you can politically give them an advantage by, for example, generating a CO2 tax or generating CO2 benefits if you use CO2. But of course, you can also improve technologies. And personally, I believe both things are needed in order to come to this desired equilibrium situation. So one of our core ideas, which especially, let's say, on the basic science, as Jay Wong mentioned, our institute is working in between basic science and applied science, and typically we have 50 cooperations per year with industry. And in the past 10 years, or in the past 10 years, 25 processes developed in our institute went at least to an industrial pilot plant stage. So we are interested in this applied perspective. But on the basic side, we are very much interested on fundamental questions like this one. And this question I want to address today a little bit more in detail. How can we make carbon-carbon bonds more efficiently? And if you're an organic chemist, you might know very well, and you might say, okay, what's the question? We have 150 years of technologies available, of research available, making carbon-carbon bonds. Clearly, in the past, we, and I mean, we means here academic scientists, we thought about elegant ways to create carbon-carbon bonds. We focused on all kinds of selectivities, atom efficiency, step efficiency, but much less about energy efficiency, carbon footprint, and feedstock price. And I think also, and this fits, therefore my talk, I believe, fits very well to this, to our general session today, because I think Lars will also talk about such things. The general carbon feedstocks for the future, if you want to come to an equilibrium situation, it's of course carbon dioxide, it's renewables, and definitely waste is a very interesting topic, and most of you quite well know the recent publication of Troels Krutstrup, where he describes the use, for example, of windmill waste. If we talk about making carbon-carbon bonds efficiency, I think it's worthwhile also having a look at biology. Because the way organic matter is created on our planet, it's basically by photosynthesis. Photosynthesis is a fantastic process. It's scientifically very inspirational, a complex process. But what it is not, and this often also people misunderstand, it's not an energy efficient process. The realistic thing is that in general, the conversion of, let's say, sunlight, the energy of sunlight, into chemical energy via photosynthesis is less than 10%, less than 8%. And the reality, at least this is what I got from biologists as an information, is the reality is for most, let's say, plants, the reality is less than 1% of the energy which initially is in sunlight is used then to produce, or is conservated as chemical energy. Therefore, it's also clear it's much more sensible, for example, if you have a certain area available, putting solar panels on that area, if you want to generate electricity, then to plant trees or other plants and then convert them to electricity. The immediate conversion is much more efficient compared to or calculated per area. But the problem is we cannot store electrons efficiently, but we can store organic matter very efficiently. So the general question is, can we create more efficient ways to create organic matter by using, let's say, for example, sunlight or other renewable energy? And one of the, let's say, the fundamental resources to generate such processes is, of course, carbon dioxide. And if you look at, let's say, high impact chemistry journals nowadays, you will see, and also in the last years, you will see a lot, let's say, of valorization of carbon dioxide. And many, I would say, synthetic, elegant examples have been demonstrated. But to be also very clear, most of these examples, they cannot be realized on, let's say, bulk scale or very large scale, because if you intrinsically produce salts or use stoichiometric, at least stoichiometric amount of metal salts to reduce, for example, carbon dioxide, it's not sensible way and not a realistic way, let's say, to create, let's say, carbon-carbon bonds from carbon dioxide at, let's say, reasonable scale. And specifically CORC addresses, and I think this is a very important point, and one of the uniqueness also of CORC, this, let's say, large scale applications of carbon dioxide. I also want to make clear here, so don't misunderstand that if you are developing a small scale process using carbon dioxide, this can be scientifically very inspirational, can be very fun, and science should make also fun. But of course, it will not solve the problem of feedstock errors and will not, let's say, be relevant to climate change. We just have to be realistic here. So when you want to use carbon dioxide on a larger scale, so there is very few, I would say, realistic chances. One is directly use what I call green electrons, so directly from, let's say, renewable energy. Another one is to use green hydrogen. That means you combine, let's say, renewable energy with, let's say, commercially available water electrolysis devices to generate green hydrogen and then use it. And there might be, I think these are the main two options. There might be a few others, but basically that's it. So when we want to create carbon-carbon bonds from carbon dioxide, I think it's important, not only important to find what I said about selectivity, reaction yield, etc., but thinking about the efficiency. And I'm not sure if you have thought about that, but interestingly, you need only one electron to form the first carbon-carbon bond from carbon dioxide. And you can basically, with using one electron or basically two electrons and two molecules of carbon dioxide, you can generate oxalate. This is the first step of making carbon-carbon bonds with two electrons. And there has been a number of publications over the past decades in this area, and we started a few years ago looking into that. There is nice electrochemical advancements in this area. But when we studied looking actually at the organometallic chemistry of this reaction, which was published, and some homogeneously catalyzed reactions, we were very surprised because all the reactions which we looked into, there were misinterpretation, there was complicated analysis, and in fact, 4 out of 5 cases were not reproducible. And we summarized this work last year in a comprehensive article where we also advised a policy how to actually look at such reactions more carefully, how to avoid misinterpretation. So if you're interested in that, I can really recommend you reading this paper. Just as one example, where we joined basically forces of the group of Andy Maverick, who published some years ago this, in principle, I would say we liked it very much when we saw that first dimerization on a bimetallic, on a bimetallic copper complex, which allows for the dimerization of carbon dioxide under very mild condition. Of course, the reaction time was long. The electrons in that case were supposed to come from sodium ascorbate, so it's clearly a model system, but it was a very nice study. But when we tried to reproduce it, it was impossible. And then we contacted Andy and his group. We teamed up to solve the problem. And in fact, we found that the main let's say feedstock for the oxalate is not the carbon dioxide which was used in these studies, but it was basically the reductant, because the corresponding copper catalyst is also a slowly acting selective catalyst for oxidizing sodium ascorbate to give carbon dioxide. This is only one example. So what I want to let's say inspire you here is there is a huge area of possibilities with, let's say, simple metal complexes with by electrochemical ways or photocatalytic ways because there is, as I said, there is nice recent advancements with copper-based electrocatalysts to look at this reaction, because the corresponding products, once you have oxalic acid, it's very stable. You can reduce it selectively to make, for example, glycolic acid. This is a relatively energy efficient reaction. It doesn't need such high temperature. It can be also done selectively. You can go also to ethylene glycol. We have shown this in some earlier work from oxalic acid derivatives. You can go from ethylene glycol, you can go to ethanol. So in principle, you have a very nice way to go from carbon dioxide via oxalates to ethanol, ethylene glycol, glycolic acid, and so on. And so build a whole carbon economy based on that. And but developing really efficient catalyst system, there is a need for that. So apart from this challenge, what is more easy and what we, but also other groups are worldwide doing is using carbon dioxide with green hydrogen. And Rauf Razak, an engineer, postdoctoral engineer in my group, together with Rui and his wife, Yuya, they developed basically a two-step process for converting carbon dioxide, hydrogen, green hydrogen mixtures to generate carbon-carbon bonds for various, I would say, industrially relevant molecules. They developed specifically a copper catalyst, which normally copper catalysts are very well known with hydrogen to make methanol. This one is tuned to give very high selectivity to generate carbon monoxide. And this carbon monoxide then can directly be utilized in all kinds of classic organic carbonylation reactions, making acids, aldehydes, alcohols, amides, and so on. And here you see some examples, let's say, of the catalyst where we reacted that on stream, 100 hours. We now did also longer term reactions. Selectivity stays very high. And this can be, or we perform this reaction easily on, let's say, multi-100 gram scale. And it's only a question of the reactor size to even go to kilogram or larger scale. Here are some specific examples where we used one of Bernhard Breit's catalysts, which he developed for hydroformylation, where we combine, you see the reactor design here. This is the selective reduction of carbon dioxide to carbon monoxide. And then this can be, as I said, done continuously for hundreds of hours. And then basically you have another device. This can be small scale or large scale here, where you do the carbonylation reactions. This reaction we also are using now for a pilot plant application, in fact, for alkoxy carbonylation type reaction, but I don't have the time to go into detail here. Instead, I want to show you some opportunities for energy storage, because as I said, in principle, let's say renewable energy is available. In Denmark, you know this very well. We have to find ways how to store the electrons better. And one of the options is, of course, to go to hydrogen. And then using that hydrogen with something else. Because of this fact that we were run out of equilibrium and we're using more and more fossil-based resources, we drastically increase the carbon dioxide content in our atmosphere. I don't have to go into detail here. You know this also very well. It's not only carbon dioxide. We also have, because of the increasing population, we have a significant increase, let's say, of methane, also N2O, for example, because of industry. And you see, all these are signs of running out of equilibrium. And if you see what have happened in the past 30 years, this is 1990, 2019, in fact, not much has happened. The the use of energy and the use of resources stayed very much the same, but this will dramatically change in the next 10 to 15 years. There I'm completely convinced, and I think consortia like CORC, they will contribute to this transition, of course. Just one example also, that climate change not only increases the temperature, which if you're living in a cold area, you might say, I don't care so much if the temperature is 1 or 2 degrees higher than in the past 50 years. No, climate change will significantly affect also food production. We just talked at the beginning of this meeting a little bit internally about the changes of climate. But what you see here, this is a collection or a summary of studies on food production, on the impact of climate change on 4 of the major agricultural crops worldwide: corn, wheat, rice, and soybeans, which provide 75% of the calories consumed worldwide. And you can see there is areas, including, I would say, Denmark, where the food production will increase because of temperature increase, but there is areas specifically, let's say, on the southern hemisphere, which will drastically be impacted by climate change, and they will be threatened by a significant decrease of food production. And as we all know, the food situation in that countries and the general economic situation is pretty bad. So this will increase the problems there. This is what we are looking into it. We're looking into, let's say, hydrogen generation from renewables. This topic, I stopped personally in my group in the last 2 years because we have a Heisenberg professorship in our institute, Robert Franke, who specifically addresses this question, and we don't want to, let's say, compete. So all the resources went basically also from my group to his group. And we are now focusing mainly on, let's say, electron storage via hydrogenation, let's say, of available resources, fundamental questions, like I said, creating carbon-carbon bond formation, and hydrogen generation from organic storage molecules. I want to give you one case study only here, because again, I'm getting pretty close to the end now, and in order to give enough time also for discussion, I will not go, let's say, too much into details. Please ask me afterwards. So for a long time, and I think we were also parallel to Gabor Laurenti, the first who proposed this concept using formic acid as a hydrogen storage material. Of course, the dehydrogenation and hydrogenation of carbon dioxide were known before, but we were the first who really basically advertised formic acid as a hydrogen storage material. We developed numerous of catalysts, including non-noble metal systems. What you see here, this is the first non-noble metal system, which highly efficiently allows for, let's say, formic acid decomposition, hydrogenation. The interesting thing is that, let's say, the hydrogen storage in formic acid is very energy efficient, because both the hydrogenation and the dehydrogenation are not highly exothermic. And if they would be highly exothermic, this would be intrinsically an energy loss in the system. Apart from the homogeneous systems, we also developed heterogeneous one. And with one of the heterogeneous developed ones, this is a cobalt MOF system. Here you see a similar base system, highly dispersed metals. Some people might call it single atom metal centers on the support. We developed, let's say, a very stable system. And one of these systems also now is in a pilot plant application with an industrial partner, Apex, where we develop a prototype, several 100-liter scale hydrogen, I have to say, which we realize currently in our new pilot plant. And we hope the company will start commercializing this next year. At least this is the goal. My last example is, again, basic research. So I touched both basic and applied research. One of the crucial issues for these applications, when you want to use carbon dioxide for hydrogen storage, for example, is that you do not release carbon dioxide after the reaction. Because if you look carefully at the reaction equation, then you not only release hydrogen when you use carbon dioxide-based hydrogen materials for hydrogen storage, you also release carbon dioxide, and you need the carbon dioxide again. So we looked at ways how we could keep the carbon dioxide in the system, in the storage device, when we release the hydrogen. And this is an example from 2 years ago, where we found that amino acids, specifically leucine and arginine, can nicely, let's say, bind carbon dioxide. You can make the corresponding formate salts, and then when you do the dehydrogenation, the system in fact stays in that. And this we developed more recently using catalysts which use multifunctionality. So they have multifunctional purposes, multifunctional sites, the active catalyst, like which is visualized here in this scheme, which are based on manganese. And you will see the performance on one of the next slides. I just want to make clear also, our group was the first who used manganese for, let's say, real hydrogenation reactions. This is an area which basically started to develop in 2016. Before, there was no example of a manganese, homogeneous manganese catalyzed hydrogenation catalyst available. In 2016, the first dehydrogenation catalyst also appeared. We published the first dehydrogenation of methanol in 2017. Since then, there was a huge development in that area, specifically on manganese. And you see the active catalyst, which we developed more recently here. You see the concept. We're using an amino acid aqueous solution. We put into that system carbon dioxide from air, so we can basically run air through the system until it's carbon dioxide saturated. So we call it charging the system with carbon dioxide. Then you use hydrogen, you heat the system to form the formate. Then you keep it at a certain pressure. If you want to release the hydrogen, you lower the temperature, you lower the pressure, and then basically hydrogen is released. More than 99.5% of the carbon dioxide stays in the system. So it's a very efficient system and can be used for the next cycle. And then you can several cycles. And the efficiency of the catalyst, these were literature works before for the hydrogenation, literature works for the dehydrogenation. And again, I just want to make clear, before 2016, nothing was known with hydrogenation and dehydrogenation with manganese catalysts. And this is our, would say, state-of-the-art system. It makes use of a ligand which Red Kemper and his group developed. It has turnover numbers of several 100,000. So the catalyst costs are not anymore, let's say, technically the limiting factor for this. It's basically the construction of the device, which we are doing now, the stability of the catalyst, and so on. So this is what I wanted to tell you. I have one last slide, because I'm very optimistic in the end. And I think in general in our society, we are too pessimistic. And as scientists, I believe we have a responsibility to bring non-biased information into the society. And very often my feeling is, at least certain parts of the society, they are way too pessimistic. If you look how we managed the pandemic flu, and if you think that more or less 100 years ago, we had a very similar flu, and that realistically, probably 20 to 100 million people died because it was simply was not calculated at time, and it was forbidden to talk about it. As you might know, the Spanish flu is called Spanish flu because the Spanish government allowed to talk openly about it. Other governments did not allow. We behaved much, much better. You can see the progress. I always like to count the fact that within 100 years, on a global scale, we doubled the life expectancy of every child which is born on this planet by a factor of at least 2. So, and this is a great thing. And sometimes we complain about our health system and all these things. And today I'm in Berlin. We have just a strike of the pharmacies today here. This is probably well justified, to be also clear, but we should be also clear the conditions 100 years ago, we are on a very good way. We have to be, I will not deny the problems, but if we focus on the problems with a bit of optimism, we can solve the problems. I'm very much convinced on that. And we should, as scientists, I think, deliver this message. This I wanted to tell you. I'm happy to answer any question. I apologize if I talk too long. And if you have questions afterwards to me, do not hesitate to mail me. I'm happy to answer.
Thank you very much, Matthias, for this